Hello viewers, in today's class we are going to discuss yet another important and very interesting definite integral, right? And in this class we are going to discuss this important integral which is 0 to 1, and the integrand is x cube divided by square root of negative of log of x, right? And here log of x is the natural log of x, right? So here the base is e, right? So what we will do here, will make use of the method of substitution, right? And then we'll apply some important results from gamma function, right? So let us start. So let us take this integral as I, right? So here, first of all, what we will do, we'll take u is equal to log of x, right? So negative of log x. So here I will assume a new variable as u, and u is equal to negative of log of x. Now let us differentiate this expression with respect to x. So du over dx is equal to negative of 1 over x, right? Okay, now see, we have u is equal to negative of log x. So from here we can write log of x is equal to minus u, and from the definition of logarithms, we can write x is equal to e raised to minus u, right? Because here the base is e. So we have this expression which connects x and u. So x is equal to e raised to minus u. So here we can take x as e raised to minus u, right? So now dx can be written as negative of e raised to minus u du, right? Okay. So now we have obtained the value of dx in terms of u. Now let us change the limits accordingly, right? So here x varies from 0 to 1. So when x is 0, then u is here negative of log of 0, right? And we know that log of 0 is not defined, so this is infinite, right? And when x is equal to 1, we have u is equal to negative of log of 1, and log of 1 is 0, so we have 0, right? So now we can write this I, this integral I in terms of u. So we have here, when x is 0, u is infinite, and when x is 1, u is equal to 0, right? And x cube is replaced by e raised to minus u raised to power 3, and here we have square root of u, right? Because negative of log x is u, and dx is replaced by minus e raised to minus u and du, right? Okay, now let us arrange this integral in a simpler way. So now we can write this integral as negative. We can take this negative sign outside the integral, and we have infinity to 0, e raised to minus 3u. This is e raised to minus 3u. Here we have minus u, so we can write it here. And then we have u raised to half, right? Okay, now what we will do here, we can interchange the limits, and we can neutralize this negative sign, because we know that a raised to a to b f of x dx is equal to negative of b to a f of x dx, right? So when we interchange the limits, then we put a negative sign in front of the integral, and here we can neutralize this negative sign by interchanging the limits, right? So we have 0 to infinity, and here we have e raised to minus 4u, and we can take this u raised to half to the numerator, so this is minus half, right? So viewers, now we have this integral, right? Now let us apply the substitution method to this integral, right? So here we are again applying the substitution method. So let us assume further that z is equal to, here we can take 4u, right? So we'll assume 4u is equal to z, right? So let us differentiate z with respect to u. So dz over du is equal to 4. That is the derivative of u with respect to u is 1. So we have 4. So we can now write dz is equal to 4 times du, right? And du can be written as dz over 4, right? Okay, now see here the limits of integration vary from 0 to infinity. So when u is 0, then obviously z is equal to 4 times 0 is 0, and when u is infinite, then z is also 4 times infinite, that is infinite, right? So now this integral can be expressed in terms of the new variable z, right? So we have 0 to infinity, and here we have e raised to minus z, and u can be replaced by z over 4, right? Because u is z over 4. So now we have here z over 4 raised to minus half, and du can be replaced by dz over 4, right? So now let us simplify this integral, right? So we can now write I as 0 to infinity. Here we have e raised to minus z, and we have z raised to minus half, and we have 4 raised to minus half, and here we have dz over 4, right? Now see, 4 raised to minus half is equal to uh, 4 raised to minus half can be written as 2 square raised to minus half. So 2 and 2 get cancelled. So we have 2 raised to minus 1, and we can take 2 raised to minus 1 to the numerator. So we have e raised to minus z, z raised to minus half. Here we have 2, then we have dz over 4, right? So 2, and we can cancel this 4 by this 2. So we have 2 to the 4, and now we can write this integral as half and 0 to infinity e raised to minus z, and z raised to minus half can be written as half minus 1, and here we have dz, right? So we have taken half outside the integral, and minus half can be written as half minus 1, right? Because here we are now going to apply the definition of gamma function. So viewers, we know that the famous Euler's integral can be written as in the form of gamma function, and we can write gamma of n is equal to 0 to infinity e raised to minus z, and here we have z raised to n minus 1 and dz, right? Where n is greater than 0, right? So the gamma function is defined like this. Gamma of n is the integral 0 to infinity e raised to minus z, z raised to n minus 1 dz, where n is greater than 0. So this is the famous integral, and if we compare this integral with this one, then we can easily see that here we have half, right? And the value of n is equal to half, right? So now this integral is equal to half times and here we have n is equal to half, so this is gamma of half, right? And we know that the value of gamma of half is square root of pi, right? So here we can replace the value of gamma of half is equal to square root of pi. So we have half times square root of pi, right? So viewers, the value of this integral I is equal to square root of pi divided by 2, right?